Happy Monday, everyone. My recording awkwardly just stopped, so now I have to redo the whole thing. It's already 15 minutes in, which is fine. It's a good thing I was doing this as a video and not a live. So I'm going to be redoing things, and you have no idea what I even just did. So this is going to be continuing 8.3 with matrices. Tomorrow I'm going to give you some practice problems. And then Wednesday, Thursday, we're going to look at matrix algebra, which is 8.4. So with that said, I can switch on over to the notes. Alright, so 8.3, this is part B. We're using matrices to solve systems of equations. Just as a quick refresher, we have seen, if I gave you a matrix such as 2, 5, 1, 3, 4, 0, we had a concept of order, which is the number of rows by the number of columns. So this is a 2 by 3 matrix. We note that each row represents, in this case, an expression. So this would be 2x plus 5y plus z. I do not say an equation because there's no vertical line for the augmented matrix. Each column represents a variable. So column 1 is always x, column 2 is always y, column 3 is always z, by convention for when we work with matrices with 3 columns. So this is 3x plus 4y. If there is a 0, that simply means that the variable has a coefficient of 0, so it just doesn't show up. We also had the idea of a square matrix, which is when we have the same number of rows by the same number of columns. So 3, 2, 0, 1, 5, 9, negative 2, half, 5. So in this case, we have 3 expressions and 3 variables. So this is a 3 by 3 square matrix. And then lastly, the main idea discussed about the terminology. We also looked at row operations, but we're going to get into those. So the last idea was discussed were augmented matrices. So we have that vertical line, which is our equals, and then we have what it equals to on the right. So this is always a constant. This would be my x, my y, and my z equals a constant. And then 0, 1, 2, 6, 8, negative 1, 2, 7. We can go back and forth between matrices and expressions or equations. So this would be 5x plus 4y plus 3z equals 4. There's no x, and this is just y, plus 2z is equal to 6. And this is 8x minus y plus 2z is equal to 7. And we call this one an augmented matrix. Now I can bring this back up. We're going to be looking primarily today at something known as row echelon form. Very important, along with reduced row echelon form, which we're going to get into in a moment. So I'm going to give us some examples and non-examples. I'm going to pause the video in a moment. So example would be, I just use 1, 2, 3 as a quick writing convention for myself. So 0, 1, 2, 0, 0, 1. So this is an example of row echelon form. 1, 2, 3, 0, 1, 2, 0, 0, 0. This is also an example. 1, 2, 3, 0, 0, 1, 0, 0, 0. And last one, 1, 0, 0, 0, 1, 0, 0, 0, 1. And then we also have some non-examples. I need to write these in a different order this time. 0, 0, 0, 1, 2, 3, 0, 1, 2. This is 1, 4, 2, 3, 0, 0, 1, 0, 0, 0. This is number 2. 0, 0, 1. This one was number 4. 1, 2, 3, 0, 1, 2. And 1, 0, 1, 1, 2, 3, 0, 1, 0. This is also a 3. If you want to take a moment to pause the video and think about what some of the patterns currently are of what makes, I shouldn't say patterns, but what are some of the rules for a row echelon form equation that would be suggested. Otherwise, we're just going to look at some of these examples as a group and discuss what makes things not an example and what the rule is. So looking at number 1, if we look here, we see we have a row of all zeros at the top, whereas in our examples, all of our non-zeros are at the bottom. So the first rule for a row echelon form matrix is that all rows of all 0 are at the bottom of the matrix. Now for rule 2, our first row is the problem. It starts with a 4. Every other row in our examples start with a 1. There's never a constant other than, or I should say a entry other than 1 in the rows in the first entry for that row. It's okay because it's a 0 because it just means the variable isn't there. So for here our first entry is a 1. For row 2 our first non-zero entry is a 1. For row 3 our first non-zero entry is a 1. So the first non-zero entry of each row must be a 1. We call this the leading 1. Alright, rule 3 is a little bit awkward to explain or to understand even. So we're going to have to try and recognize what's going on. So looking at these two examples, well, in row 1 I have a 0, a 0, a 1. In row 2 I have a 1, a 2, a 3. And then row 3 I have a 0, a 1, a 2. This is almost like this first example, but there's one slight issue. The question is, what is that issue, and how can we express it? Over here, We have 1, 0, 1, 1, 2, 3, 0, 1, 0. Again, this is almost like something we've seen. Not entirely, since I now have a different first row than anything else I had before. But it causes the same problem. And that problem is, if we look particularly at this example, anytime we have a leading 1, every entry beneath it needs to be a 0. So I have 1 in the first column, everything beneath it is 0. In my second column, row 2 gives me the 1 for my leading 1. So everything beneath row 2 now in column 2 has to be 0. I'm actually quickly draw another example. I need to save my text. Got my brush. Another example of a row echelon form matrix would be 0, 1, 2, 0, 0, 1, 0, 0, 0. This would actually be another good example for us to look at. In this case, well, I don't have a leading 1 in column 1, so everything in column 1 is going to be 0. So if I never have a leading 1 in a row, everything beneath our row that already has a leading 1 should be 0. And this is visible in this guy as well. So I have my leading 1 in column 1, so everything beneath it should be a 0. I don't have another leading 1 until column 3, and I'm starting at row 2. So everything in row 2, so everything in column 2, starting from row 2, should be 0. In words, and this is something you can apply kind of recursively, so I'm actually going to write it recursively. So the leading 1 in row n is more to the left than the leading 1. Actually, I don't need to say the leading 1. Is more to the left than row n plus 1. So the leading 1, say in row 1, is more to the left than row 2. So this first example, well, here's 1, it's more to the left than row 2. That's true. In this case, my leading 1 in row 1 is in column 3, but that's to the right of row 2, so that's why this one fails. In this guy, the leading 1 in row 1 is the same column as row 2, so it fails because it has to be more to the left, not equal, more than. And this one also tells us everything below a leading 1 is 0. Now, the last thing, which is a reduced row echelon form, comes from the actual example. Anytime I look at a leading 1, I see it has zeros below it. If I look at this leading 1, it's got zeros below it, and it also has all zeros above it. In this last row, there's nothing below it, so we can't have anything below, but everything above is a 0. So to be a row echelon form, each column contains a leading 1 and no other entries. So everything above a leading, I shouldn't, actually, nope, that's not right. Scratch that. That's technically not worded correctly. I'm going to write the way that I prefer to write it, which is that each entry above and below a leading 1 is 0. Because I can actually show you an example that would have broken that, how that was written out. But what I had wrong in that one is I was saying each row, it should read each column containing a leading 1 has no other entries. Before I had said each row, it should have said each column. That's where I went wrong. So in this case, since I have a leading 1, there's no other entries. I have a leading 1 here, so there's no other entries. Now, something that's interesting about this, that I'm going to write another example for. Move this down and lock it. And then move to layer 1 and brush. This is a example of reduced row echelon form. If I don't have, so we'll say 0. In this case, I have a leading 1 in column 1, so everything below it is 0. I don't have a leading 1 in column 2. So it's okay that I have the 2 here. This is still reduced row echelon form. On that note, I'm going to say go take a quick break, stretch for a moment, get up and walk in like a circle real quick. We're about to get into the actual solving for systems of equations using matrices now. Okay. So there are two methods we use. Both were found by Gauss. So I'm going to switch to text because I have some text I need to type. So going from a matrix to row echelon, or I should say going to reduced row echelon. The best thing to do to solve a system of equations is to turn our matrix into a reduced row echelon. You could solve just using row echelon in substitution. If I go back, so in this case, this one's the best one. So over here I have a value for y, or for z. So this might be like z is equal to 3. I could then plug in z to then find y. I would then have z and y to be able to find x. With reduced row echelon form though, such as this one, and this is actually an important thing to note, this diagonal from the top left to the bottom right, you may see now called as the diagonal or the main diagonal. So when we have a main diagonal of all 1s, that's really helpful if we also have all non-zeros. Well, if we have all zeros elsewhere. So you think about this, I have z equals something, I would have y equals something, and I'd have x equals something. So I'd already know my answers for my variables just by inspection if I had an augmented matrix. So this is our best option to get to. So that's why I'm saying going from a matrix to reduced row echelon form, but you could solve just from row echelon.